The transition of digital infrastructure from Earth to orbit represents a fundamental shift in how humanity manages the exponential growth of artificial intelligence, AI, and data processing. Space data centers, SDCs, are emerging as a software-driven multi-tenant solution to the mounting physical and ecological limits of terrestrial computing. As foundation model training and hyperscale AI services drive ground data centers toward unprecedented power densities, the industry faces critical bottlenecks in energy supply, cooling water availability, and land access. By deploying computing infrastructure beyond the atmosphere, operators aim to leverage near-constant solar irradiance and the infinite heat sink of deep space to decouple computational scaling from Earth's ecological constraints. This new frontier is characterized by a rapid shift from theoretical white papers to operational hardware, billion-dollar funding rounds, and massive regulatory filings for mega constellations. The terrestrial bottleneck and the case for space. The primary driver for moving data centers into orbit is the exhaustion of terrestrial resources. Large hyperscale data centers currently operate at power levels near 100 megawatts, with global projections suggesting data center energy demand will exceed 1,000 terawatt-hours by 2026, roughly equivalent to the total consumption of Japan. Terrestrial data centers are on track to consume between 8% and 10% of global electricity by 2030. This surge has led several U.S. states, including New York and Oklahoma, to impose emergency grid moratoriums on new data center connections. Furthermore, permitting and building new terrestrial data centers and energy projects can take up to 5 years, a timeline that cannot keep pace with the AI revolution. In contrast, space offers several fundamental physics advantages. In the correct orbit, such as a dawn-dusk, sun-synchronous low Earth orbit, LEO, solar panels can be up to 8 times more productive than on Earth and produce power nearly continuously. This environment eliminates the need for heavy onboard batteries and provides a stable, predictable energy source independent of day-night cycles or weather conditions. Additionally, ground-based cooling systems consume billions of gallons of fresh water annually, accounting for approximately 58% of the electricity used by terrestrial facilities. Space-based systems can reject waste heat directly into the vacuum through thermal radiation, consuming zero water in the process. Major commercial players and the orbital race. The orbital data center market is experiencing a period of intense competition, with the sector projected to grow from $1.77 billion in 2029 to approximately $39.09 billion by 2035. By early 2026, several major organizations had already deployed hardware or committed substantial funding to the race. StarCloud, formerly Lumen Orbit, has emerged as one of the most prominent players, achieving unicorn status just 17 months after completing the Y Combinator accelerator. In November 2025, the company launched its StarCloud 1 satellite, which successfully carried the first NVIDIA H100 GPU into orbit, delivering a 100x increase in spaceborne AI compute. StarCloud 1 demonstrated historic firsts, including the first orbital AI training, running NanoGPT on the works of Shakespeare, and the first orbital inference on Google's Gemini model. The company has raised $200 million to date and has filed for an 88,000 satellite constellation designed to process data in orbit. Its next milestone, StarCloud 2, is set for late 2026 and will feature the largest commercial deployable radiator sent to space, generating 100x the power of its predecessor. In February 2026, SpaceX and xAI merged into a $1.25 trillion entity, aiming for tighter integration between launch systems, satellite internet, and AI growth. SpaceX filed an FCC application for a massive 1 million satellite orbital data center system operating between 500 and 2,000 kilometers altitude. CEO Elon Musk has stated that within 2 to 3 years, space will be the lowest cost environment to generate AI compute, facilitating unprecedented scale in model training and data processing. The system will rely on high bandwidth optical intersatellite links and integration with the existing Starlink network. Announced in November 2025, Project Suncatcher is Google's moonshot to scale machine learning compute in space. The project envisions compact constellations of solar-powered satellites equipped with Google TPUs, V6E Trillium, and connected by free space optical links. Google has already validated its TPU hardware for radiation tolerance and demonstrated bench-scale optical links achieving 1.6 TPs per sec total bandwidth. A partnership with Planet Labs aims to launch 2 prototype satellites by early 2027 to test distributed ML tasks in orbit. Axiom Space is developing a cloud-enabled orbital data center intended for its future commercial space station. In January 2026, Axiom deployed 2 data center nodes aboard Kepler communications relay satellites. These nodes evolved from prototypes that ran cloud computing, AI, and cybersecurity applications on the International Space Station in 2025. Kepler's constellation operates as an IP-based mesh network with dynamic routing, providing the connectivity backbone for Axiom's ODC nodes. Institutional feasibility and international efforts. Governmental and institutional studies have confirmed the viability of STCs while highlighting necessary technological leaps. The ASCEND study, coordinated by Thales Alenia Space and funded by the European Commission, analyzed the technical and environmental benefits of space clouds. The study defined a 10 megawatts minimum viable product and set an objective of 1 gigawatt total capacity by 2050. Ascend concluded that SDCs are a promising alternative to terrestrial assets but require the development of a launcher 10 times less emissive over its life cycle to achieve true carbon neutrality. Internationally, the UAE Space Agency unveiled its National Space Data Center in 2022 to promote innovation and scientific research. In India, Neve Cloud partnered with Agnikul Cosmos to launch over 600 orbital edge data centers using rocket upper stages as hosting platforms. Meanwhile, the Chinese government has proposed a sovereign network of 200,000 satellites with on-orbit processing capability, including 2,800 dedicated AI computing satellites. Thermodynamic and physical challenges of space computing. Deploying high-density silicon in a vacuum presents severe engineering hurdles, primarily related to heat dissipation and radiation. In orbit, the absence of air means convection is impossible. All heat generated by processors must be rejected exclusively via thermal radiation to the deep space cold sink. This process is governed by the Stefan Boltzmann law, where radiated power depends on surface emissivity and the fourth power of the absolute temperature. To maintain semiconductor temperatures below standard limits, 75 degrees Celsius to 100 degrees Celsius, radiator surface temperatures must be kept relatively low, which restricts the amount of heat that can be rejected per unit area. For a 1 gigawatt capacity system, modeling indicates a total radiator panel area of approximately 4.6 square kilometers is required. To manage these loads, systems are moving towards single-phase and two-phase pumped loops, the latter leveraging the latent heat of vaporization to absorb significantly more heat per unit mass. Space-based electronics are exposed to total ionizing dose damage and single-event effects, such as bit flips or destructive latch-ups caused by high-energy particle strikes. Traditional radiation-hardened chips often lag several generations behind the state-of-the-art. Modern SDCs instead utilize software-defined hardening on commercial off-the-shelf hardware. Methods include triple modular redundancy, where calculations are run in parallel, and dynamic voltage and frequency scaling, which dials down processor speeds when radiation anomalies are detected. The HPE Spaceborne Computer 1 mission validated this approach, spending 615 days on the ISS and surviving over 6,800 passes through the highly radioactive South Atlantic anomaly with zero-bit errors. Connectivity and communication paradigms. Connecting SDCs to global backbones requires high-bandwidth, low-latency links. Free-space optical laser communications are favored over radio frequency because they can pack data up to 100 times more densely and provide better physical security due to their narrow beamwidth. However, the gap between the petabit-scale internal exchange of ground data centers and the gigabit-scale capacity of space links remains a critical bottleneck. To address this, researchers are exploring semantic communication, which focuses on meaning fidelity rather than bit-level accuracy. By transmitting only task-relevant representations extracted from large datasets, semantic systems can reduce communication overhead by up to 60% compared to raw data transmission. This is particularly useful for in-orbit AI workloads where only high-impact features or analytic insights need to be returned to Earth. The value of in-orbit processing was demonstrated in an ISS experiment by Microsoft Azure Space and HPE. By simulating the processing of a 200 gigabyte raw human genome sequencer file directly on the Spaceborne Computer 2, researchers filtered the data down to a 13 megabytes file of critical mutations. This 15,000-fold reduction allowed a dataset that would have taken 2 years to download to be transmitted in under 2 minutes. The lunar frontier and interplanetary storage. Expansion is not limited to Earth orbit. Companies are targeting the Moon as a site for resilient data storage and disaster recovery. Lonestar Data Holdings successfully tested data storage and edge processing en route to the Moon in March 2025 aboard Intuitive Machines lander. The payload featured an 8 terabytes enterprise-grade SSD certified for spaceflight. Lonestar plans to deploy future servers inside lunar lava tubes, which provide natural basalt shielding against extreme surface temperature swings, 127 degrees Celsius to 173 degrees Celsius, and cosmic radiation. The company envisions the Moon and the Earth-Moon L1 Lagrange point as the ultimate off-Earth storage solutions for critical digital assets. Economic viability and the mass tax. The commercial success of SDCs depends on the cost per watt of usable compute in orbit reaching parity with terrestrial alternatives. While SDCs offer free power and cooling, which accounts for roughly 58% of terrestrial operational costs, they face high upfront capital expenditures. Engineer Andrew McCallip developed a base case cost model comparing a 1 gigawatt LEO solar compute fleet to a terrestrial gas turbine facility. The model estimated a total capex of $51.1 billion for the orbital fleet versus $15.9 billion for the ground facility. At a launch cost of $500 per kilogram, the levelized cost of orbital compute is nearly 3 times higher than terrestrial alternatives. Strategic parity depends almost entirely on the reduction of launch costs. If heavy-lift vehicles like SpaceX's Starship can bring costs below $100 per kilogram, SDCs could reach cost parity for specific workloads within the 2028 to 2030 window. Furthermore, the algorithmic paradox presents a risk. Physical satellite hardware lifespans, typically 5 to 7 years, are mismatched with the rapid pace of software innovation. AI compute efficiency improves roughly 3x per year, meaning orbital hardware could become obsolete well before its launch costs are amortized. Success likely requires vertically integrated models and modular architectures that support robotic in-orbit hardware upgrades. Environmental and sustainability considerations. While SDCs are marketed as a solution to AI's sustainability crisis, their full life cycle impact is complex. The ESpace model from Saarland University found that when launch emissions, hardware manufacturing, and atmospheric re-entry are included, orbital compute has an effective carbon intensity of 800 to 1,500 gram CO2e per kilowatt hour, which is worse than many country-level grids on Earth. True sustainability requires reaching the ascent threshold, where launch vehicles emit no more than 1.9 kilograms of CO2 per kilogram of payload. Current rockets exceed this by 10 to 25 times. Launching the necessary thousands of rockets releases combustion products directly into the chemically fragile stratosphere. Kerosene-burning engines emit black carbon, soot, which can linger for 4 years and act as a thermal blanket, potentially raising stratospheric temperatures by up to 2.0 degrees Celsius. Additionally, the design-to-demise principle for debris mitigation requires satellites to burn up on re-entry. Vaporizing thousands of metallic satellites annually could inject over 30,000 tons of material into the atmosphere by 2040. Scientists have already detected spacecraft origin metals in 10% of stratospheric aerosols, a figure that could reach 50% as constellations scale, potentially accelerating ozone destruction and altering wind patterns. Conclusion: a hybrid computing future. The orbital data center race has moved from concept to competition in record time, with 3 companies already operating hardware in orbit as of early 2026. However, SDCs are not expected to replace terrestrial infrastructure entirely. Instead, they will function as a highly specialized redundant tier of a hybrid global computing network. The industry's near-term trajectory points to Wave 1 applications 2025 to 2030, focusing on niche, high-value workloads like real-time Earth observation analytics, maritime tracking, and defense surveillance where processing data near the sensor is critical. Wave 2 2030 to 2035 may see a shift toward energy-intensive AI training as launch economics improve. Ultimately, the successful scaling of this off-world compute layer depends on overcoming profound thermodynamic constraints, achieving radical reductions in launch costs, and mitigating the long-term environmental impacts of mega-constellation life cycles. As the industry pushes toward a gigawatt-scale future, these orbital platforms may redefine the boundaries of digital infrastructure and inspire a new era of interplanetary commerce.